It had some problems, and I'm interested in fixing things. I'm interested in things that are engineering-wise that can, hey, how do you fix something in space? This one was designed to. I would love to do one on the Hubble, on James Webb, which is a much nicer, newer telescope. If I did that, then we probably wouldn't want to go back and look at anything on Hubble. But Hubble still contributes, and it had been upgraded over the years, so it has some very good imagery that comes from it. And there's some newer telescopes out there as well. So debating on whether we put in space again, we'd have to go through that. So we're going to talk about this first, and then after that, we're going to talk about killer asteroids at 10 that may or may not hit and destroy the world. So there seems to be a lot of them in the news lately, so I thought I would talk about that a little bit. All righty, so what is Hubble telescope? And I've heard about the mirror problems. I've talked to people who worked with it, and they said that was incredibly terrible. There was a lot of people going to get some medical help after this. They got it finally fixed because it was really, really rough on everybody. So we'll talk about that a little bit. We'll look at the problems they had. We'll look at how Hubble works itself. I'm dressed in white, black, well, white and white. I'm no color because Hubble doesn't see in color. So I don't know why I've got red socks on, but they're my Captain American socks. Anyway, so we'll look at that. We'll learn some tools that we need to try and figure out how far stuff is away and why Hubble is unique, and the telescopes are unique at looking so far out and how they do that. And then we're going to go back about 15 billion years in the past. So we're going to see 15 billion or more years what happened that time ago. And some cool pictures. So it started out, my dog was the person who likes to look at my presentations first when I give them, and it was like, who's Edwin Hubble? I'm like, well, that's a good question. So he's an extragalactic astronomer. I have to say that 2 or 3 times. And I think he was in the 50s. He came up with the idea that at that time, when they looked through telescopes, they saw these little pockets of dust out there, and they thought, oh, it's just pockets of dust. I mean, we're talking about galaxies, what we're talking about. But he's the one that figured out that those are actually galaxies and came up with one of the first ways to figure out how far away they were. And he's credited with the idea of a recession of the galaxies, that everything's moving away. And so one of the things that you walk away from here today is that everything you see in the night sky is not there. It's moving. It's moving very fast. We're moving. We're going 1,000 miles an hour right now as the Earth spins. The Earth's spinning around the Earth. The Earth's going around the sun. Everything's moving. Everything's moving. The sun's moving through the galaxy's moving through the universe. Nothing's where it's at. And in Star Trek, if they were able to get from point A to point B in a day, it wouldn't be there. So there's a whole other problem there. And this is called Hubble's law. All right, so this is a slide that in one day when he got this slide and they figured out what was actually on this slide, it changed everything. It changed the size of the universe in one day. This is a 4-inch by 4-inch glass plate. That's how they took pictures at the time. He was looking at the Andromeda Galaxy. He did not know it was the Andromeda Galaxy, really. He was trying to figure that out. And if you have 1 trillion stars, then you're going to see routinely some go supernova. I mean, the odds are low that you'll see one, but they're not 1 trillion to 1. I mean, they're more. The odds are easier they'll see one. So this slide actually has 3 different stars that have gone supernova, and he's marked them with an end, as in nova. Then he crosses this one out because it isn't a nova. It's something called a Cepheid variable. So it's actually getting brighter and dimmer and brighter and dimmer. So it's different than all the other stars, and so he starts digging into why that's happening. And he has someone help him. There's a lady named Harriet Leavitt, and she has figured out that if you look at something that's varying in brightness, if you measure the period, you can figure out how far away it is by how bright it is. You can come up with the brightness, and he tied that to, so when he did this and they started adding things up, he found out that this was actually a galaxy 2.5 million light years away. And we'll talk about, does everybody know what a light year is? I'm going to go into it later, but heads up, it's a distance of length. It's a measurement in space, just like that. So he came up with, he measured the period, and then he came up with the idea that it's 2.5 million. So it is not part of our Milky Way galaxy here. And our Milky Way galaxy is only 150,000 light years across. So everything jumped in one day from 150,000 light years across to 2.5 million, and that's just the nearest one to us. So the galaxy just jumped in size real big. And so we built this telescope and we named it after him. This is a pictured on orbit. It's actually been through a couple repairs because it has the newer panels on there. Here's the door they close when they don't want to get hit by things, or they would want to go spin it around where they don't look at the Earth or the sun. And this is where all the instruments are, and this is where the mirror is. So these are going to be like puzzle pieces up here, and I'm going to tell you a bunch of pieces, and at the end we'll put them together, and hopefully they'll help you understand a few things. But each puzzle piece, if you learn something in the puzzle piece, then you're good. So, and there's no real test at the end, even though I may give you a grade. So by the numbers, this was launched. It's about 12 tons, so it's kind of a big payload. It's 13 feet by 38 feet, so about the size of a school bus. Overall, the cost of the telescope and the repairs that they put into it, they're pushing about $16 billion for this telescope. That's going to come in comparison later when I show you one on the Earth and what it can do, but there's problems with both places, so being in both places. They had 5 repair missions. We're going to talk about a couple of them, and it's nearing its end of life. So, this is it going out to the pad on top of a school bus. So, okay, this is the payload canister over here. And it will lay down or stand up, and they usually put the payload in there and then take that out the pad so it doesn't get nice and dirty. The school bus is only used for weekends. All right, so why put a telescope in space? Why would you do that? Well, on the ground, the atmosphere filters out a lot of stuff. So it filters out X-rays and gamma rays, and a lot of the UV and ultraviolet are knocked out, and they don't make it down to the surface. So if you have a telescope and you're looking, you don't get those. There's a lot of dust and movement in the air, so it makes your pictures kind of shake around. So that's why they put telescopes on top of mountains and get them up there where the air is clear. Has anybody been to Hawaii? You've been up on one of the mountains there. They've got some stuff up there. And as you're driving up, you go through the cloud layer, and you get on top, and it's like all white and everything out there. So kind of bad if you wanted to see the ocean, but so that's some real problems. It creates some blur. It has some atmospheric dust. These are some problems on Earth that they have to deal with, and they're coming up with ways on the ground to deal with that, which makes it easier to have a telescope on the ground. Now, if you put it in space, you can get rid of some of those problems. It's very clear. You get all of the wavelengths of light through there. No dust, no light. It's very clear detail, very, very costly, almost impossible to maintain. So you have to pick what you want. There's things that you can do in space that you can't do on the ground. There's things on the ground that you can do that you can't do in space. But in any event, we don't really want to see some of this stuff because it's bad for our skin if we get some of this stuff down. So the atmosphere is really protecting us quite a bit. So there was a problem when they got on orbit and they saw some of the first pictures coming back, and I'm sure a few of the engineers went in a corner and just sat down and cried in a ball because it was fuzzy, and they're like, what did we do wrong? So it turns out that the guys that were grinding the telescope had an instrument to measure what they were doing, and the calibration was off. So they did a very good job of grinding the lens. Does anybody know the name of the company? I got pictures over here, so that's the wrong pictures. Who said Perkin-Elmer? So the name of the company was Perkin-Elmer, and they weren't really getting along. Who said that? Okay, this is for you, and the other person that probably said it, yours is on number 2. So some pictures of some constellations and stuff. So we'll keep that out there. So they ground it. They did a good job grinding it, except for they ground it wrong, which was a real problem when they got up on orbit. It turns out that NASA and the contractor were mad at each other, and so they really didn't communicate at all when something came up. They just decided, hey, and they wanted to do a test, and NASA said, we're already over budget, we're not paying for it. That test would have found it, and they would have used the backup mirror that Kodak had made, but they didn't do that. But luckily it was ground perfectly wrong. I'll cover these guys' faces up since they're not too happy with what they're doing. They're using the tool to measure it incorrectly. This is the tool that I believe was calibrated incorrectly. And here's them all proudly standing in front of their mirror. And so now we've got to go figure out how to fix it. And so the idea came up of, since it's ground perfectly wrong, maybe we can put glasses on it. So this is their start thinking process on changing the focal length and putting glasses on it. This is a picture of one of the astronauts. The Hubble Space Telescope is made with doors on it so that it can be opened and serviced. So anybody see the program on TV last night? They talked about 5 minutes about this, I think. One of the problems that I didn't know about, I knew some of it, but I knew most of what they said. This was just interesting. Everything went great. They went to go close those doors and they wouldn't close. Now they said, hey, we've got a ratchet strap here. We can pull them tight with a ratchet strap. And they're like, you're going to destroy our telescope. And after debating for hours on whether they should use it or not, the launch director or the director just said, go ahead and do it. And we'll see what happens. And they got them to close. But they would have not been able to, the instruments would have been in danger of being damaged if they didn't get the doors closed. So we're going to have to fix some things. This is called CoStar. It's corrective. It's basically glasses. It's a 600 pounds size of refrigerator glasses. Doesn't really weigh 600 pounds, but when you take in orbit and you've got something that weighs, it's still got mass, so it's hard to move around. It's easy to push, but it has to get going and you have to hold it to stop. And so they're going to take this out of storage and they're going to push it into the telescope, into one of these bays right here. And they're going to pull out some other instruments and stick those back in. And it's got 5 sets of glasses on it. And these are adjustable, micro-adjustable, so even if there's a little bit of mistake, they can actually move them around and get them right where they need to be to focus it. So they kind of learned a bit. Additionally, they're going to put in a different type of sensor that's wider, that shows a bigger field, something normally they would look at like through a straw, but now they're going to look at they can now look at something the size of the moon. That's going to come back a little bit later too. And here we go, we've got it fixed. It doesn't look like a great improvement, but the idea comes in the ability to separate 2 objects at great distance, and you can't do that in this. But as you dive in here, you can start to see you can get things that are very close together. Any astronomers in the room? What's that called? Arcs of separation or something like that? Somebody say yes. Okay. All right, whoever, well, we'll give away more pictures. So Kodak was making one at the same time. Theirs was perfect. They checked it after the fact. They offered to check their Lockheed Martin ones and PerkinElmer's, and they didn't want to do it. So they were going to each check each other's to make sure they were in good shape. They would have found it at that time, but they did not do that. And this one was kept in storage for a long time for no reason. Then they finally threw it away in the trash, which I understand. So, okay, we're going to talk about another problem now. This is Mike Messineo. He's one of the astronauts. He's been up there a few times. And they were, earlier you saw the yellow handles, that they're handholds. Well, they had to get one off to open a specific door. They got 3 of the screws out, and there's only 4, and they couldn't get the last screw out. And so they went through plan A, through plan B, through plan C, and finally I'll just let him tell you. So this is the handle here. It's actually in a museum somewhere. It just would not come off. So I'll just go ahead and show the article with him in it, and I'll come back one.
Planet Houston, we don't have video right now, but we're ready.
Okay, man, so you have a go.
There we go.
So, disposal bag, please.
So he just decided, he said, well, just let me break it off. All kinds of problems. The engineers on the ground were going nuts. They were saying, hey, if debris comes off when you break it, it goes into our billion-dollar telescope. Our telescope's ruined. If it snaps off and hits you and pokes in your suit, you die. So they started putting tape around it, and he's just like, hey, look, let me try this. Well, you can't just pull on it. You have to have something to hold you, so that's why he was kind of yanking on it a bit. Engineers got on a table and took one and pulled it up and broke and said it comes off at about 60 pounds. So they really weren't worried about him breaking it, but they were worried about him getting hurt. And about right when they went to go do it, the ground had a blackout. They didn't have no comm, so he went ahead and did it anyway. And so when they came back out of the blackout, they were like, yay, we got it done. Everybody was very happy. So now they get to go work on it. So that was one of the problems. So they got through that, and then they just didn't put the handle back on. Why put it back after all that? But it came off nice and clean and allowed them to continue on with their work. But he's now known as the Space Hulk for that. So Catherine Thornton, one of the opportunities that they have when you work at the Space Center is that the crews after the launch will come back and talk to groups. And so they'll come in one or two at a time, and they'll go to an office, and you gather 20 or 30 people around, and they basically are saying thank you for getting us to space and home without killing us. And, okay, thank you for giving us a good ride is what they usually say. And you can ask them all kinds of questions. When I operated in the LCC, I got to usher them to areas and spend a lot of time with a lot of the astronauts. She specifically was there, and we asked her the typical question, what was your highlight of the mission? And she said, well, her job was to stand there and hold one of the solar panels while they disconnected it. So let's go ahead and see what happens from there. So this is her on the end of the Canadian? A's, is that right? Who's Canadian? Okay. So very big deal. Thank you, Canada, on the arm. So she's out there, and they start extending. So they disconnect the solar panel, and they start pushing it all the way out. So she's as far as you can get away from the shuttle. She can't see it; it's behind her, and she's got this big old solar panel on the end of it by the tail. So a couple of things are going on there. When she pushed it in the center starts to move before the ends, and so it flapped away and flew away. She said it looked like a big bird in space. And then the second thing is, in 90 minutes, it's going to come right back and hit you. So quickly, the shuttle will do a maneuver to pull away from that so it's not in the same orbit as that. And then eventually that will come in and land and burn up, like we saw a couple of days ago with something in the sky. Everybody who saw that? There was something that burned in. I'm pretty sure it was some kind of spacecraft, which is quite odd. But they usually plan to land them in the middle of the ocean where no one is. I don't think they expected us to be here. So, all right, so that was one of the cooler repairs. They did 5 repairs. What they're doing in all those repairs is they're upgrading things like the gyro and the electronics. It was designed like back in the 80s and built and put up. It took a long time to design it. So during that time, many, many things improved, and they had increased the capability to get it to the point where it's getting the same quality of images that James Webb is, but James Webb has a lot bigger mirror. It's like twice the size or 3 times the size of this one, so they can distinguish more brilliantly between two, but it still gets really good pictures, deep. So we need some tools. We're going to come up with an astronomical unit, which I talked about, and then the light year. So does everybody remember what we talked about, the astronomical unit the other day? So if the distance from the sun to the Earth is an astronomical unit. Nice thing. So if we put our ship there, and we called it a one-ship astronomical unit, so we could get some scale to how far that is. That's 93 million miles, by the way. 92 to 94 million miles from there to there. So somewhere on board, probably by the elevators, is Mercury and Venus. I don't know, Venus is way hotter, so if you find a hot place on the ship, that's probably where Venus is. And then just off the end here is Mars. So now the next question for a picture is, how many astronomical units away is Pluto? Who over here? I heard a number. Was it 7? What was it? I'm deaf. 70. That's actually pretty close. It's 40. I mean, that's pretty close. So, and you can see where all the kind of the planets around in here. So we need a lot of ships to get there. So we'll go ahead and keep going. So how far is it to the next nearest planet? How many astronomical units is it to the next planet? Proxima Centauri b and Alpha Centauri. I take wrong answers too. How many? 10,000. So let's see. 10,000 is a pretty good answer. 300,000. So that's pretty close. So in astronomical terms, it's like, what's the difference? So if you were on our little ship here thing, how far away would that be? So you would have to go around the world twice to get to Proxima Centauri b. So, all right, so that's kind of the astronomical unit. So I think we're good with that, at least I hope. If not, then we'll figure out another way to talk about it. So now we're going to talk about light year. I needed a little bit of help. I couldn't use the other guy, so we used Bugs. He's now named Bugs Armstrong instead of Buzz Lightyear. So I think one of my kids came up with that name. I don't know. Maybe my grandkids. So what we're talking about is the distance. It's a distance measurement. So it's the distance that light travels in 1 year. So that's light year. So light goes 186,000 miles per second. And so after 1 year of travel, it has gone 1 light year. And that's not too far, about 6 trillion miles. I mean, if you want to be careful, it's 5, 8, 6, 5, that's lots of numbers. But basically, we'll just stick with 6 trillion miles. So we're talking about the nearest planet is over 4 times 6, 24 trillion miles away. I'm sure we can get there in no time. So, if you use AU, that's easy. The distance from the sun is 1 AU, but it's only 8.3 minutes, which is light year minutes. We talked about that the other day. The moon's 1.3 light year seconds. The nearest star is 4.2 light years away, and then 2.5 million light years. So the chances, if you were going the speed of light, it's going to take you 2.5 million years to get to the next galaxy. I don't think we're doing that. So if you want to get on a cruise ship and do that, you're not going to make it. If you're going to another at 4.2 years to get to the nearest star, that's still a pretty long time going the speed of light. So that's a pretty long time, pretty long cruise. So we're talking about seeing these things that are as they were, when we look at Andromeda, and you can go outside and you can see it. If you have no lights, you can look up and you can find it, and you can actually see it with a naked eye without a lens. If you have your phone, you can get a nice picture of it. I did that a couple days ago. And so this stuff is a long way away, and it's not there. It's been moving for 2.5 million years. So let's just figure out what it would take to get to the nearest planet, Proxima Centauri b, and hopefully when we get there that it has a habitable environment for us to live on, which probably does not. So we're going to just ignore quite a few things in physics and math because that's just too much to do, and it doesn't really help. I'm just trying to tell you how far away it is. So we're going to need a ship. I'll build one out of what's readily available. We have some solids and some space station parts and just what we have. And you're going to need like lots of Walmarts of food and water and much, much, much alcohol, because there's not really a lot to do. So you take a good book with you that you want to read 1,000 times, I guess. And then we're going to look at, okay, what's the fastest thing we've got moving right now? Solar Parker Probe, we'll just round it to 500,000 miles an hour, which is pretty quick. So the question is, how long does it take to get there? And I don't even know the answer, so I do know the answer. I'm lying. But if somebody gives me an answer, then we'll know for sure in a second. 500 light years, 500 years? 500 years to get there. So in our best spacecraft we've got, we're thinking it's 500 years to get there. Who wants to be on? And then when you get there, you don't even know if this is your picture here, the Hubble Space Telescope. I know it is because it says it on the back. So let's see how long. So we're going to go there and hope we don't run into anything on the way. 6,000 to 10,000 years, and those are wrong numbers because I left out all that other stuff. If you run into a dust particle in there, it's going to go through your spaceship like a knife through butter. If you run into an asteroid, it's going to take you out. Even if you don't run into anything, you're going to run into things like monoatomic oxygen, single electrons, and they're slowly going to sandblast away the front of your spacecraft over the time, the 10,000 years plus that it takes you to get there. So when it comes down to aliens, did we want to talk about aliens? This is the closest place that's not in our solar system, is here. They're going to have to, it's going to take them, our best technology, more than 10,000 years to get here. If they can do that, then we should be afraid of them because, well, I told you the other day, if we don't understand something, don't be afraid of it. But they're probably going to have a lot more technology than us to get here. And since we've only been awake technology-wise for a couple of 100 years, really, yeah, we're probably not going to win that. So, well, now let's try and figure out, and this is impossible again, the size of the universe. Somehow we can figure out. It's been, like I said, everything's moving. The universe is expanding. And so the question becomes, this is part of Hubble's law, that everything's moving apart. So how big is it? And it's expanding. How big is it going to be? Is it going to go out and stop expanding? Or is it going to get out and stop and then fall back and collapse and then do it again? So there's lots of people out there trying to answer that question. I think the prevailing theory is it's just going to keep going and never go back to fall back in. But it's, we've been, I think at the top here, we're thinking this from here to here right now is around 100 billion light years across. That's quite a size to it. So when I say no bang, it means no noise. In space, there's no noise. That's not true. We have radio telescopes that can look and hear at radio frequencies, and we turn that down to something we can hear, and so there's noise. But everything we see out there is on a spectrum, and so we can see light for just a small part of the spectrum that we can see. Bees and things can see more. We'll talk about that. But it does make a bang of a sort. We're going to take this to a little bit extreme. If we boil down a light year into the size of a grain of sand, if we start looking at it from that perspective, how many grains of sand would we need to get across the universe? Okay, this is just for exercise shape. So somebody estimated that there were 7.5 quintillion, and I don't even know, I had to look that up to see how big that is, grains of sand on all the beaches of all the world. That's a lot of sand, by the way. So the question becomes, how much sand would we need? How many beaches of sand do you think we would need? So I've got a picture here for somebody who wants to guess, and I'm not expecting the right answer, so. 20? 20. So 20 is the answer. So we need 20 beaches of sand, right? That's what we're thinking? Okay, so how many earthfuls of sand would we need? Since we got that answer, let's go ahead and, so we've got 20 beaches, but now let's turn it up to the scale of how many earths is full of sand would we need. So I'll let somebody else guess. So your 20 is just a little low, but you get a picture here for that someplace. You're on number 11. A million? 100,000. All right, so let's see how many we need here. 120,000 earths full of beaches full of all the sand on 120,000 earths to do that. That's a lot. And the real question becomes, so there's an actual calculation here I did right there. So plus or minus 2 or 3 miles. I'm sure it was off by a couple. Now, the universe is expanding. So every day you'd have to throw on another beach because it's expanding so fast that you'd have to throw on another beach just about every day to keep up with it. Expanding. So let's go ahead and take a look at the Milky Way, which when you look up, looks like grains of sand. So that kind of looks like grains of sand, doesn't it? So each one of those is a star? No. Each one of those is a galaxy. All of them. 10,000, they estimated 10,000 galaxies in this picture. And if you're to take that grain of sand and hold it up in the air, that's the size of the piece of sky that they're looking at. They found the darkest spot in the sky that they could find, and they looked at that for, what did it say, 11 days at night. Every night they took pictures of it, and this would cover this entire chart if you held it in the sky. And there is they counted 10,000 galaxies. Each one in there has anywhere from 100 to a trillion stars. So that's a lot. You can see that this is what a spiral galaxy. You can start, when you start digging in and looking, you can see some of these that look like this are just turned sideways. That's just sideways. You can see the bulge right there. This is what they look like from through a telescope, specifically at a specific galaxy. So I know our brains are a bit shorted out right now. Mine is. So this is a normal spiral galaxy. It's about 13 million light years away. M51. There's so many we can only give them numbers. Now who did an experiment in high school or even elementary school where you made a little model of the universe and all the little planets went around the sun? Somebody had to do it. Hit this lady in the back there. Did you do one? So this is a butterfly nebula here for you. on number 9. Did you get a good grade on that? Just for heck? No. This is why you became what'd you become? HR. This is why she now works in HR, not astronomy. So I look at something like this, and this is the model that we were taught. You know, everything kind of rolls around each other, looks pretty cool, and for most part, nobody needs any more unless you start doing some orbital mechanics or decide you want to go in a spaceship for 10,000 years and try and get to Alpha Centauri that's not there anymore, that's been moving every time you're going there. All right, so everything is moving around each other. So does the moon orbit the Earth? Yes or no? No. Sorry, doesn't. The Earth and the moon orbit each other, and they go around the sun. So this picture is actually still wrong. As the moon goes by, it's pulling on the Earth. We know that because of the tides, and it actually wobbles back and forth. And here's a picture of what Jupiter and Saturn do to the sun. This is the center point of the whole rotational system. And they're actually pulling the sun away from that center of rotation point. So nothing is, when you talk about something orbit, and they got to figure this out when they launch payloads into space, that everything's moving. You got to know that. You don't need to know that to do most of the jobs that we do. But that's what's happening with just the impact of Jupiter and Saturn. But you've got all the other smaller planets in there, and Jupiter is yanking on all those as well. So these aren't going in a straight circle either. The sun is also pulling them off, and they're on elliptical orbits. They're not on round orbits. So there's all kinds of stuff going on. And then all that is flying around the sun that's moving through our galaxy. So this gets quite complicated, and if you haven't shorted out yet, then I'm going to keep going, and we'll finish this short. So this is a rendering of our galaxy. And this is the path that our actual sun is kind of taking. I don't think they've actually measured, because this is like a thick $60 million wobble trail through here. But even our sun is wobbling around, and everything in here is moving. So what we see and what we've been taught is a little different. Does it matter? No, unless you're doing some astronomy and start looking for stuff, and then you start worrying about this stuff, which causes me headaches. Here's what I'm talking about. So you're on the Earth. You're looking at something 65,000 light years away. You see a star. Is the star there? The answer is no, right? Where's the star? Well, it's been moving for 65,000. That light has taken 65,000 years to get here, whichever direction it's moving. Now it's way over here, 65. So you're looking here, but it's actually all the way over here. So the light is kind of bending to get here. It is bending and it isn't bending. So it looks like it's bending, but it actually is bending according to Mr. Einstein guy, so theory of relativity and stuff. So it actually is bending. There was some writings that were by a Japanese astronomer. I need to go find out a little more about this. I don't know what they wrote it on, sheepskin or something, but about 6,000 years ago, and they saw something blow up. So we go start searching for that. Well, we know it's not here. Where is it? It's going to be over here. So that's what it looks like now. They saw this, we see this. This is 65,000 light years across because it's been expanding for 65,000 years. Okay, got our space rabbit, I got my dog. Look at something pretty. Are you going to look pretty for us? Yes. Okay, this is a ring nebula. Okay, everybody take a brain break. I'll get a drink of water. We can look at the picture. That's quite a bit to take in. So what I'm trying to do here is show you that there's more to a lot of things than we've been taught, and there's no need for us to know more than, but if you're just trying to drive yourself crazy like me, then you'll try and figure them out. Let's see if I can get back on time here. I got about 10 minutes. So this is why I'm dressed like this. This is a picture from the Hubble telescope. It's in black and white, because Hubble sees in black and white. But what it does is it takes filters at different frequencies. So it takes pictures at different frequencies, and then it knows what color we see them, and it reassigns those pictures the color that we normally see as at that frequency. Our visual spectrum is very, very small. There's a whole infrared spectrum over here that snakes can see, because they see it with sensors, not their eyes necessarily. But there's a whole big spectrum over here. One of the guys studying prisms, and I brought some prisms to do this, he was trying to see if each color had a different temperature. So he put one thermometer off to the side as a baseline to see how far things were changing. It was the hottest one. And he's like, well, how could it be hotter than the other ones? Well, that's because infrared is heat. And so he's putting his thermometer over here where it's hot. And the other thermometers are in here, and it's hotter. And that's how he discovered there's other light there that we can't see. And then if you're a bee, I always wondered why a bee can go to a flower and know that there's pollen there, and the next bees know not to go there. Well, they can see an ultraviolet, and they can see that another bee's already been there, so they don't go to the same one over and over again. So when we take a picture, we have these pictures, different frequencies. So we'll take this frequency from the Hubble, and this one, and there's reasons why we pick these specifically. And then we know that everything we see here should be blue, and everything we should hear green, and everything we should hear is red. But those actually tell us if there's sulfur or oxygen or hydrogen in the environment that we're looking at. These are spectral lines that tell us that. So that's why we look there. And we have lots of spacecraft up, some that look in different frequencies. So this is the frequency spectrum here. That's the visible range. And we have infrared, microwave, radio, television, and audio's way over here, audio that we hear, way down the list. And we're looking from the ground and space. And then we take all these things and we stack them up after we take all these pictures and we put them together. And now they're getting faster at that. You can see the visual spectrum is very small. And then we stack them together, and this is what we get. So when people ask, is that a real color picture? Well, Hubble can't. Only visual telescopes that you look through with your eye can you see the colors. When you look at Hubble, you're seeing something that's stacked together that has more visual range than we can see. And they've assigned them colors. So they're pretty pictures, and they're accurate within respect of some frame of reference. So we're going to go into a couple of the galaxies now, and we're going to start using some of that data we have to figure out. So this is two galaxies. They're in a fight with each other, and they're kind of ripping each other apart. They're 65 million light years away, and they've been in a fight for quite a while. So let's see what happens to them. So our Andromeda galaxy is coming towards our Milky Way. So this is our Milky Way, and that's Andromeda. They're obviously animated. There's another light battle of some kind. Sorry about that. So I talked to a friend of mine who's a planetary scientist. He says, we are going to get in a fight, so everybody should go home and worry about that. It's going to be about 4.5 billion years, about the same time that our sun gobbles us up. So it's really a gloomy future for us. But he said it's highly likely that when these two fight, that nothing will hit each other. Gravity will pull things around, but there's so much space, as we've been talking about, the distance from here to the nearest star to the nearest galaxy. There's so much space between things that they will likely just come in, interact, and then they will join together to become some new. Somebody actually knows the name of this. What's the new combined galaxy name? Does anybody know that? Last time I had a 12-year-old tell me, I'm like, there's a name for it. I can't remember what the name is. Come tell me later if you know. So, what is it? Okay, anyway. All right, so we have time to see a couple of pictures. I got like 6 minutes, so let's just run through. Here's all our puzzle pieces. I think we've learned a few things. We may have learned some things, maybe not. You can give me a grade later. So these are just some of the pictures that are coming out of Hubble. Some of them are actually, I'll just go ahead and say, some of them are actually out of James Webb, but I'm not going to say that out loud. This is the Little Dumbbell Nebula. So this is something that exploded. I had somebody helping me explain this the other day. So the way that the space environment with UV and all the light flying through comes off of it. But if you can imagine that something blew up here and is now coming apart, and this is what it looks like. Here's two more that are going to get in a fight. I don't know what that is. So we'll go ahead and do a dive in with the telescope. One more.
Now, a new Hubble image shows the region in unprecedented detail. Capturing the multicolored glow of gas clouds, wispy tendrils of dark cosmic dust, and the rust-colored elephant's trunks of the nebula's famous pillars. With these new images comes better contrast and a clearer view for astronomers to study how the structure of the pillars is changing over time. Hubble also has an additional New Year treat for us. The telescope gazed at the same area in infrared light, allowing it to pierce through the obscuring dust and gas and unveil a more unfamiliar but just as amazing view of the pillars.
So the takeaway there is the newer technology. Somebody asked me the other day, how come my camera can look at the aurora borealis and it can see green and blue when my eyes cannot? That's because the camera has better sensors in it than your eye in some respects. And that's what we're doing here. We're pulling out some of the different frequencies, and we can actually see through that dust from the nebula. This is a dwarf or an irregular galaxy, not quite as spiral as ours. Here's a two-armed spiral galaxy, 50 million light years away. It says it's 750,000 light years across. So how many people think there might be life out in one of these? I believe certain ways, but I have to believe that it's possible, so. What do you think this is named? Okay, very good guess. Eye of God. We showed one of these earlier. I don't think it was the same one. Now, this is if you were to hold a balloon up to the light, you could not see through the edge because the balloon is actually thicker there. In the center, it's thinner, and that's what we're seeing here. This is the same all the way around, but it's very thin right in here, and we can see through it a lot easier, whereas this, we're looking through a whole edge of it, so that's why it comes out that way. And something in there is what blew up a long time ago. Another spiral galaxy. We could look at these all day long. Okay, names. All right, I'm going to give away a picture if somebody gets this right. What is it? Devil? Okay, who said Mickey Mouse? But I'm gonna give it to the first one, but very good back there. So it's called the Heart Nebula or Running Dog. Mouse, dog, pretty close. So this is on number 7, and then you're going to be on number 8. So can you see a smile in there or something? I don't know. Maybe it's a heart. I don't know. So this is the eye of God here. So that's it for the pictures for me for right now. I find it fascinating that all this stuff is out there, and it wants me to go out and buy a telescope. But do you realize what kind of telescope you have to buy to see this? I mean, you can see some things that are pretty cool, but these are like, billion-dollar telescopes. And this is called the Pillar of Creations. We said, I think there's a picture somewhere I have of those, so I've given away some of those. This is some of the old imagery. This is some of the old imagery from Hubble. And here's some of the newer upgraded sensor ones. And James Webb's is taking pictures like this. And you can look at these all day long. I mean, there are thousands of images that are available like this to look at. So just a few final thoughts, and we'll kind of close this one out since I'm right on time. What's the reason for all this size of stuff? Why is it so big? How do we fit into all that? And if this is the universe, all we know, what's that? What is that? You know, it isn't this. This is empty space mostly. You know, what's beyond what we can see? Why is everything moving so fast? Where's it going? What's it in a hurry to do? I guess it's not in a hurry. And then you think about the blink of time in what? 75 years, 100 years that we've actually been able to, maybe 150 years, that we've 200 years. It's still a blink of all this 100 million years, billion years, and it's just a blink that we've been able to see that. In the next show, we're going to talk about asteroids and meteors and where they've come from. I don't know about these things. We can talk about those too if you like. So I have some personal views about that. If you want to talk to them, I'm still in the ship. I'm on here for another day or so you can find me and pester me. I don't mind. But I have questions about this as well. So I have time for a couple of questions. I think I got a couple of minutes. This is me and my son's dog. And so I'll take a couple of questions. I don't really have any pictures to give you right now. Yes, sir.
Are they going to do an upgrade 6 on the Hubble?
They have no way to service Hubble anymore. The shuttle was their opportunity to service it, and they don't have a shuttle flying anymore. And right now, the current payloads that they fly are not able to get there or do the repairs. So,
SpaceX had offered to.
Well, they probably offered, but the question then becomes, would you spend money to upgrade?